In modern machine learning, the heavy lifting increasingly happens on GPUs. As model size and data scale exploded, the GPU evolved from a graphics accelerator into core infrastructure for This chapter opens with that big picture, so you can see why low-level performance now matters for everyday practitioners. Most developers experience GPUs through high-level frameworks, which is productive, but also creates a black box feeling. You move tensors to CUDA and everything gets faster, until the day you need a custom, fused operation and performance falls apart. That is where understanding the stack becomes essential. The central gap is clear. Python frameworks maximize speed of development, while CUDA maximizes control. Moving directly from one to the other can break your workflow and slow iteration. Triton exists to bridge this exact gap by letting you write custom kernels in a Python-first style. Triton is both a language and a compiler. You express kernel logic with a Python-embedded eDSL, and Triton compiles it into efficient GPU code for the active backend. The goal is to keep you in the same environment while still enabling serious performance work. A key idea is that compilation happens in process, usually on the first kernel call. You do not have to leave your notebook, build a separate extension, and rewire your project each time you test an optimization idea. That tighter loop is one reason Triton adoption has grown quickly. Not every bottleneck needs Triton. Always profile first and use framework-level optimization where possible. But when a hot path remains slow after torch.compile, or when you need a custom fused op not available by default, Triton becomes a practical next step with a strong performance-to-effort ratio. In the GPU programming spectrum, Triton sits in the middle. More control than framework-only code, much less friction than handwritten CUDA. It complements both ends rather than replacing them. This position is exactly why it works well for research teams and production ML engineers. You already see Triton in the wild. PyTorch compilation paths, training libraries, and serving engines rely on it for high-performance kernels. That means learning Triton is not niche knowledge anymore. It is increasingly part of the modern GPU engineering toolkit. This tiny kernel sketch shows the core mental model. The program ID picks which tile this kernel instance owns. Offsets select elements for that tile. The mask handles boundaries, and load compute store performs the actual operation. You describe tiled work in Python, and Triton maps it efficiently to hardware. Before going deeper, separate concurrency from parallelism. Concurrency structures many tasks so they can make progress. Parallelism executes many tasks at the same time. Tensor workloads gain most from parallel execution, which is exactly the strength of GPU hardware. CPUs and GPUs are engineered for different goals. CPUs focus on minimizing latency for a few powerful threads. GPUs focus on maximizing throughput across many lightweight threads. Understanding this design difference helps explain why GPU kernels require different optimization thinking. The execution model vocabulary matters: thread, warp, block, grid, and streaming multiprocessor. Triton abstracts much of the thread-level complexity, but these concepts still explain where performance goes. The better your mental map, the faster you can diagnose bottlenecks. Triton encourages tile-level programming. You define work for one tile and launch a grid that covers the tensor. The runtime distributes blocks across streaming multiprocessors until all tiles finish. This block-first view is a major shift from writing scalar thread code manually. Every Triton kernel follows a lifecycle. Define in Python, compile on first call, launch from host, execute on device. This path explains startup cost, caching behavior, and why repeated launches with the same shapes are usually much faster after warm-up. Performance is often limited by data movement, not arithmetic. Registers are extremely fast, while global memory is much slower. Good kernel design reduces expensive memory traffic and keeps useful data close to compute. This memory perspective is foundational for all later optimization work. That is your Chapter 1 foundation: why GPUs matter, what Triton is, where it fits, and how to think about execution and memory. In the next hands-on lesson, we will move from concepts to building and running your first Triton kernel step by step. If this clarified Triton for you, subscribe to Life of Geeks. Next video is fully practical. We write, launch, and benchmark a real kernel together. Comment Triton if you want the starter checklist.